Okay, so this is Ramin. The purpose of our final project is to improve the previous model that we had. And to do that, I'll have to first get you through the derivation of these two facts. We have the Slinky that we are trying to explain how the Slinky falls, and not necessarily the masses attached by the spring. So we are more concerned about the Slinky itself than the model. And that's why it's versus time. We want to see how each point changes position versus time. So now, first, let's see why these two hold true. So why, we might think that the spring constant is the same throughout the whole Slinky, but that is not true. It depends on the length, as I said. The length of the Slinky and the K, the spring constant, are inversely proportional. So as one increases, the other one goes down. To make you understand that, we have a Slinky at its relaxed position, length L, and if I extend it by an amount delta x, I get a force, and if I call this the positive direction, I get a force of k delta x. Now, if I have two of these Slinkies, and I connect them together as I have it here, right? The length has doubled, right? And this spring becomes more elastic, and its K drops by a factor of 2. And why is that? Because for this spring, to get me the same amount of force, to reach the same amount of tension in two of these, I have to extend this by delta x and this by delta x. And therefore, you can see that the extension is 2 delta x. K, 2k delta x. So because the extension is larger, in other words, to get the same force, if I have a longer Slinky of the same property, of the same quality, I have to expand it more. And because this expansion, that length, that displacement is larger, the K must be smaller, because their displacement and K are inversely proportional as well. Here you can see that if I have this Slinky combination of these, with length 2L, the K drops by a factor of 2, and it's more elastic. So here, if I am concerned about the masses, 4 masses at 3 different points, equidistant from each other, the K of each of the 3 sections must be 3K. It's squared if it has a smaller length. For now.
Okay, so as previously mentioned, the purpose of our model is to drive a better mathematical and graphical model of the Slinky drop phenomenon. So that, as we saw in the graph of the model that we previously generated, the top mass graphically falls below the second mass, and the second falls below the third. So we don't really want that to happen. We want a more realistic model of the position of each point along the Slinky versus time. So how do we deal with that is by including collision, because as we know, the top clump collides with every rung as it's falling down. And the general equation for any collision involves momentum, and this is the general formula for the conservation of momentum. Basically says that the sum of the momentums of 2 objects before the collision are going to be the same as the sum of their momentum afterwards. So momentum is conserved. And then we know 2 facts, that every point along the Slinky have the same mass, and 1 is equal to m2, and the same with our model, so they have all the same mass. And the velocity afterwards are going to be the same. So this velocity basically represents right after the top mass collides with the second mass. At this point, it's going to have the velocity of the average. Then after a time, delta t, as it's passing, as it's falling down, it has another velocity that can be calculated knowing the acceleration and the velocity, as we previously had in our model. And then these two collide with the third mass, and the same thing must happen at this point, the same momentum formulas and derivations that we had. and then they fall and hit the fourth mass. So this is how we arrive at the formula, and then we get a general formula.
For our experiment, in order to accurately measure the Slinky drop, we attached stickers, actually no, not stickers, we attached tape to each section of the rung, and we colored them so we'd be able to see them in the video. However, when we took the video and then we uploaded it onto the editor, the frames jumped around, so we couldn't get an accurate measurement that we could use to effectively test our model.
Hello, and we are gonna test Slinkies in water. Why would we test Slinkies in water? For one purpose only. Would the bottom of the Slinky remain motionless in a different medium, which is water?
Go.
Where was I? Okay, we saw the video, and as you can see, the external medium does not influence the Slinky drop. And you must wonder why, obviously, you're a scientist, and it's because tension is less due to buoyancy upward, so that makes the velocity go slower, and at more time for the bottom to remain motionless. So the bottom stays still as the top pump is just still falling, as observed in water. As you saw, it didn't really change.
I shouldn't say that, just have to cut it because yeah, that's V-sub. V-sub, and then this, okay, so here's go. And this is the general formula that we get. Because the top clump, as it's falling on top of each rung, it's taking it with its same velocity. It's taking it with okay, you have to cut that part, but okay, just, okay. So, because as we know, the top clump is falling, okay, so continue filming. Let me think about it. You don't have to edit this, right? Okay. Cool.
Nope.
So
We can't go to the moon, so we can't test that. So we just kind of have to rely on water this time. So
what was the moon thing for?
because it's a different medium.
The velocities are going to be the same, and that's called an inelastic collision. So if we rearrange this, formula.
One take, pretty much. Are you still recording?
Yes.